Okay, well, let's take a look at AP Topic 9.7 and what you must know from it. And we're going to be talking about polar form. And we're going to do the first part of AP Topic 9.7 right now, which is really more of an introduction to polar form, which you might already be familiar with from pre-calculus. We'll get into the calculus part of polar form with the second video that will follow this about AP 9.7. So here we go. Hopefully you know some of this stuff. If not, a quick overview. Feel free to pause it and think through things, or look up extra resources as you need to. So polar coordinates are graphed on what's called a polar plane, and that's this over here on the right side of the screen. So that's different from a coordinate plane or a Cartesian coordinate plane, like an XY graph. And so we have a few things that are important. At the middle, instead of having an origin, we have what's called the pole. And then almost always, in the cases that we'll see, we go off to the right from the pole, and that's called the polar axis. And so that's where we start counting our degrees. So basically, a point in the polar plane will be r comma theta, where r is the radius, meaning how far away from the pole, from the center are we. And theta is what is our angle from the polar axis. So for instance, this point is 1 comma pi fourths. It is 1 unit away from the pole, and counting from the polar axis, it is at 45 degrees or at pi fourths. This point is, we could call it a couple of things. First of all, we could say it's 2 away and 5 pi thirds when counting all the way this way. Or another thing is that a radius can be negative. If we kind of draw this up through here, we would find out that that distance is negative 2 when we go to 2 pi thirds. So that's a little bit different, and so just keep in mind that a negative radius goes the other way from the pole, and your angle then you're going to have to measure to where that radius goes if it wasn't negative. So a little bit different there. Okay, well, let's do a little bit of practice here on a couple things. So we want to be able to convert back and forth between polar coordinates and rectangular coordinates. Let's start right here with number 4. So we want to convert from a polar coordinate, let's say 4 comma pi halves, to the corresponding rectangular point. And so we're going to use these formulas. And these formulas you're going to use maybe a couple of times throughout your AP Calculus work, so you'll want to memorize them. That x is represented by r times cosine of theta, and y is r times sine of theta. So to find the x, we're going to go 4 times cosine of pi halves, and of course that would be 4 times 0, gives us an x of 0. And then y is going to be 4 times sine of pi halves. And of course that is, that is 1. So 4 times 1 gives us a y value of 4. So the xy, or regular rectangular point, would be 0, comma 4. So that's, you're going to use these equations to go from polar to rectangular. Now going backwards from rectangular to polar is a little more complicated. We need to take our r and our theta and turn them into, let's say that again. We need to take our x and our y and turn it into an r and a theta. Well, what is r? R is the radius. What is the radius? Radius is the distance to the pole, or in an XY graph, the distance to the center, the origin. And so in your math classes for lots of years, you've found distance between 2 points. And specifically, if we're going to use the origin, we would just say x squared plus y squared, the square root of all that. Now, what's theta? Theta is the angle to where we're going. Well, how do we find that angle? Well, think about it like this. If this is an xy coordinate, we have a point here, then that angle to there, we can make a triangle. And if we think about trying to find this angle down here that I shaded in on the bottom left, let me highlight it with yellow. If we want to find that angle right there, then, well, what do we know? We know the x and we know the y, so we know that that's the opposite and adjacent, so tangent of that angle equals y over x. So we're going to find the arctangent of y over x, and that'll give us the angle. So that's what's stated here. So a little bit more work to convert from a rectangular, just a regular xy point, to a polar coordinate. So let's actually practice that once. So let's suppose that we have a a rectangular coordinate of 1, 1. Okay, so we need to find the radius first, and I made it pretty easy just for us to see the process. So 1 squared for x plus 1 squared for y is 1 plus 1 square root of 2. So there's our radius, square root of 2. Our angle, or theta, is going to be the arctangent of y divided by x, 1 divided by 1. And if you think about your unit circle, that is 45 degrees, or pi over 4. So square root of 2 comma pi fourths is the polar coordinate. Okay, number 6 and 7 here, we can convert rectangular equations to polar equations, doing the same thing, the same idea. You're going to substitute for your x and y's with the formulas from above and solve for your r, and then, so on and so forth. Number 7, we can convert from polar to rectangular, same idea. Not a big deal. It's just following the same stuff, and except for if you're going to make it into an equation, once you get your x and your y, you're going to solve for the y. Okay, well, all of that is really just preliminary. You may not have to actually do that on a AP calculus exam. It could pop into the middle of a problem, but feel free to practice those things. That's not really calculus necessarily. We get more interested in calculus when looking at the graphs of polar equations. Let's think about a couple of basic things, and then we'll look at what you really have to know, and you're going to have to spend a little bit of time memorizing. But here we go. Let's start basic. First of all, circles will just be r equals a number. So the equation r equals 4 is, well, all the points that are 4 away, right? So it's just a circle. 4 away there, 4 away there. Lines that pass through the origin are going to be theta equals some number a, so where a is the angle that you're going away from the origin, and then you would just draw a line through it. So if we have maybe a polar plane here, and then we had some angle going up to here, well, the line would just be through that angle. Now, straight lines that don't pass through the origin will require a little bit more work, using our same r cosine of theta and r sine of theta to equal some type of number where n's a number, and you might use some trig identities to kind of manipulate things and such like that to get straight lines there. And even more complex graphs, you just might have to create a table of values and plug in different angles, get out your r's, and kind of do it an old-fashioned way. Okay, well, all of that is okay. For AP Calculus, not as interesting as the next page. And you do need to know what's on this last piece. And it's kind of a lot to process, but you need to know these, because in the following lessons we're going to work with polar graphs, and these are the kinds of polar graphs that we work with a lot, in addition to regular circles. So here we go. Reading at the top, there are some special polar graphs that you need to familiarize yourself with. We're going to start with the first, which is called a limacon. And a limacon it looks like a circle, but it has a little dip here. And some people call it a heart graph. Now, I've given you different versions of cosine and sine so you can see what happens. So cosine, a positive cosine goes to the right, but subtracting cosine takes the limacon to the left. Positive sine makes the limacon go up, negative sine makes the limacon go down. Now, I made all these numbers 1 and 1, and I'd invite you to log into like Desmos or something and play around with some of these numbers. But what you'll find is that whenever the number in front of sine or cosine is bigger than the number added in front, then your limacon gets this inner loop. And that's really interesting and really kind of cool. And so I would invite you to go to a website like Desmos and just plug in some different numbers and get some different size loops. Switch between sine and cosine so you can switch the orientation of the graph, switch between positive and negative, and see what happens with these limicons. Now, if this first front number that's all 1, if that becomes 0, then it's going to become some type of circle graph. Okay, so let's talk about the second type, which is called a rose curve. And so there's some examples of rose curves. Think of the flower rose, and so we call each of those coming off the pole a petal. And so the first thing I want you to notice, and I do want to point out that I have the wrong thing on my screen here for this equation. It should be 1 sine 4 theta. The first thing I want you to notice is that if the number in front of theta is odd, then that actually tells us how many petals we have. So in the first one on the left, we have 3 petals, and on the second one there, we have 5 petals. Now, if the number's even, that's more interesting, because if the number is even, then that doesn't mean that we have that many petals. It means we double that. So you can actually see that with 6 theta, we actually have 12 petals, if you would count all those, and 4 theta, we have 8 petals. So that's the first thing to know. Now, what we need to know is that also on a cosine graph, the petal will go to the right. So all of our cosine graphs, the petal starts to the right. So let me kind of illustrate that, going to the right and going to the right. But on our sine graphs, the answer is not quite as clear cut. Sometimes, basically, what happens is instead of going to the right, it's always shifted away from the right just a little bit. And so that's the difference between cosine and sine and how you can tell that. All right, there are circles at the bottom. I alluded to those a moment ago whenever we looked at the limicons. But basically, 1 cosine, 1 sine, that number in front will make the circle bigger. Notice that, like before, cosine goes to the right and left. Sine generally goes up and down. And finally, there's one more called the limnoscate. The square root of cosine and square root of sine may or may not encounter those in calculus, but square root of cosine 2 theta goes left and right. Square root of sine 2 theta has that same idea with the rose petals. It's kind of off. It's not exactly on any of the axes that we would expect. All right, so that's just an introduction to polar form. And with the next videos, we will actually use calculus with the polar forms. But what I do want to emphasize is that you do need to know these different polar graphs, so make sure you're familiar with those. All right, thank you.